Hey, this is OXDF, and I'm looking at the Advent of Code 2015, Day 20, Infinite Elves and Infinite Houses. And we're doing it in Rust, so let's take a look at the challenge. Um, Basically, Santa has elves deliver him presents by hands from an infinite number of houses numbered 1, 2, 3, 4, etc. Each elf has a number, and they go to houses based on that number. So elf 1 goes to all of them, elf 2 goes to the even houses, elf 3 goes to 3, 6, 9. Basically, they start, they count up. They go, if the house is divisible by their number, they stop at it. Um, each elf delivers presents equal to 10 times his or her number at each house. So you can get these examples here. House 1 got 10 presents because house elf 1 went there. House 2 got elf 2 and elf 1, so that's 10 plus 20. House 3 got 1 and 3, not 2, so that's 10 plus 30. House 4 gets 1, 2, and 4, so that's 10, 20, and 30, or 1, 10, 30, and 40, 10, 20, 40 for 70, etc. So let's see. What is the lowest house number of the house that has at least as many presents as your puzzle input? And my puzzle input is 36 million. So we got to find out which house, what's the first house that gets 36 million presents. So as far as this one goes, this was one of those challenges that is kind of common in Advent of Code, although we haven't seen one before in 2015, I don't think, where the algorithm, figuring out the algorithm is much more important than the coding itself. Once you get the algorithm, the coding just kind of comes along. And the important thing to remember here is memory versus CPU. I'll show an example with memory based at the end, I think, but or sorry, with CPU based, where we try to do a lot of calculations. But the thing to remember here is we have a lot of memory at our hands, and we should really not be afraid to use it. So what I'm going to do here is I'm going to create a vector that is the input divided by 10 long. So 36 million, so let's say 3.6 million long. And the reason I'm going to go to that number is that's too many. But if I have got 3.6 million and I divide that by 10, or I've got 10 per house, 10 per, right? So let's just say the first elf 3.6 million is going to visit that house first, and it's going to drop off 3.6 million presents, which is 10 times that is 336 million, which is enough to satisfy the challenge. So I know if I go that far, I'm going to satisfy the challenge. I'm fairly confident I'm going to get there long before, but it's a safe thing to do. And so why can we afford to do this? Well, let's say I keep a vector of 3.6 million U sizes, unsized integers that are 64 bytes long. Even if I do that, I could say 3.6 million times 64 bytes, and I get 230 million. Now, 230 million bytes is 230 megabytes, and I'm running on a computer with 64 gigabytes. That's a lot, but even if you've got 16 gigabytes, this is a fraction of one of those. So this is nothing. We can handle this no problem. So let's go ahead and jump over to VS Code. I'm going to use my GenDay script here to do day 20. I covered this in detail in day 0, the intro video, but it just pulls my input.txt and starts me a little stub here. Today's one of those days we're going to modify this. So we're going to say, we'll call this like min presence equals that. And we will then do this and we'll parse. It's getting long enough that maybe we should make it look pretty. Trim it, parse it. Probably going to have to go and specify this is going to be a U size. And then we will need to unwrap it. And I think that'll give us a thing. Let me pause for a second to fix my extension. All right, looks like the extension's back. That's good. So we've got min presence written as a U size, and we know that's going to be 36 million. So what we need to do here is we need to start thinking about, like I said, we're going to make a vector of houses. So we'll say let mut houses equals vec, and that is going to be, we're going to initialize it to all zeros, and we're going to do present, not present, min presence divided by 10 to get the right amount. Again, I think we need far less than that, but why save memory at this point? And so now we're going to say for elf id in one dot houses dot, oh, let's undo that, dot houses dot len, ooh, len. So looping over every house, we'll say let mut locate, oh sorry, every elf ID. Because remember, again, we probably aren't going to really need to go to elf ID 36 million, but why not, right? So we'll say let mut location equals the elf ID. And that's because each elf is going to start at their location, right? So the first house elf 5 goes to is house 5. So it's going to start at location 5. And we'll say while location is less than houses.len. So while they can keep going, we will houses location, we'll drop off some presents, plus equals elf ID times 10, because they drop off 10 presents, 10 times their ID. And then we will location plus equals elf ID. So basically what we're going to say here is the elf is going to drop off 10 times as many as their elf ID at the house, and then they're going to jump to the next house they would visit, which is plus their elf ID. And as soon as that location gets bigger than the array, we'll break out of there. And so now we've got an array from house 1 to house 36 million that has all the house presents delivered. So what do we do next? We just need to come down here and we can say houses dot iter. Let's turn it into an iterator. And we'll use this dot position function. And what this is basically going to do is we give it, so it's going to step through the iterator, giving us, let's say, x. And it's going to stop and tell us a position when we find some condition we give, which in this case is x is greater than present, I always want to say presence, min presence. I'm not sure why I'm not getting autocomplete anymore. And as soon as that's the case, it'll stop and return the index. And we might need to do an unwrap on that. Let's see. Option size. Yep, so let's do an unwrap. And we're going to have to borrow. Yep, let's borrow here. And of course, we don't need a semicolon. And it might be that simple. Cargo run. We're definitely going to want to do release here since we're doing a lot. Let's see, 831,600 sounds like the answer to me. Let's check it out. That is the answer we got. So that pretty nice. Part 2, the elves decide they don't want to visit infinite number of houses. Instead, each elf will stop delivering after 50 houses. So to make up for it, they're now going to deliver 11 times their number. So we need to do the same thing with those changes. And so really we're gonna basically do the same thing here. We'll say let mut houses 2 equals spec 0, and this time we'll do min presence is still the same, but we're dividing by 11. We'll do for elf ID in 1 houses 2 dot len, and then this time we're going to say let mut location equals elf ID, just like before. Now we're going to say let mut delivered equals 0. So we'll see how many is this elf delivered. Start off with 0. And then we'll say while location is less than houses 2 dot len and delivered less than 50, because if we've delivered 50, we want to stop. Now we'll just say houses 2 the location plus equals elf ID times 11, and we'll say location plus equals elf ID, and we'll say delivered, and I mean this is kind of like delivered equals like number of houses delivered is 1, and we should have a very similar loop here to do the same kind of thing here. So we'll say houses 2 dot iter dot position. We take some x and we stop when x is greater than or equal to min presence. And we unwrap. Let's see what we get. Oh, we don't like something. We are missing a close parenthesis. No, we're not. How's position? Unwrap. We're not missing. We shouldn't have a semicolon. That's why. Nope. Let's see. Something up here. Well, location is less than. Let's see. What is this? Comparisons cannot be changed. Oh, why am I doing and there? That's just some typos. Typo problems, the best kind. 884520 884520. So we're done. And I almost forgot. I said I was going to look at going maybe the alternative route here, and let's go ahead and talk about that now. So my gut instinct when I'm looking at this problem is to say, let's take a function like we'll call like a function sum of factors, and we'll take an n, which is a u size, and we'll return a u size like that. And now we do something like dot one dot dot n plus one. We can do that into an iterator. And then we can do dot filter so that we're going to only get the ones we could say like, so for any x, let's see, n mod x equals 0. That's a good filter. And then we can do maybe a fold to sum these up. We could probably just do a sum. Is that going to work? Maybe we have to do into iter. I think that works. We can test this out a little bit. We're gonna go ahead and we'll still keep our min presence here, but then we're gonna get rid of all the rest of the work we did. Comment that out. And so let's do some tests here. We can do print line like that. We can do comma, sum of factors, and let's pick something we know like 8. And we will run this. It's not gonna be happy that we didn't use our presence, but so 15, 8, that'd be 1 plus 8 is 9, plus 2 plus 4 is 15. So that worked well, and it worked pretty fast, right? I'm gonna go ahead and underscore this so it stopped yelling at me. So we can do that. We can time this. Doesn't feel too slow. What if we do like 1,000,000? Still not too bad. We did that in 0.2 of a second. We do 10 million. Does it get slower? 0.2 seconds. So we're getting bigger, right? So now we're doing 0.2 seconds per run. The challenge is going to become, let's see. So what I really want to do here then is I would say like let mut I equals, we could probably start higher, but it doesn't matter, right? We don't go too high. Equals 1, and then we can say while sum of factors on I is less than, we'll start with like 1,000, right? It's less than 1,000. And we want to multiply that by 10 actually, right? So because they drop 10 presents at every house, it's less than 1,000. Then we are going to I plus equals 1, and that's it. And so now we will just print line, and let's run that. And so like so the first house that gets 1,000 presents is house 48. We could do some math on that, but that feels not crazy. And it ran quickly. So if we go to 10,000 presents, first house is house 360, still very fast. Let's go ahead and make it, what if we do 1,000,000 houses? Like that. So if we want to do 1,000,000 houses, we're getting up close to a second now, but we're still getting an answer fairly quickly. What if we had 10 million houses? And you're like, oh, that can't be that much more, it's factor 10, right? The problem is that now we just added 9 million more runs through. And not only 9 million more runs, but those runs are now going to go up to, went from being 1 million long to being 10 million long. So we added an extra 9 million runs that are all 10 times as long as the previous one. So that actually is going to be significantly longer. And we can see we're still running down here. I wonder how long this is going to take. I might have to pause and let it come back. But so this is the problem with going this route. I believe we can actually get a solution this way. In fact, once this finishes and I get a time, so 41 seconds, not terrible. But now if we go up from 1 million to 10 million, we went from less than a second to 41 seconds. Now we're going to go up to 36 million, because that's our puzzle input here is 36 million. So we could just do min presence, and I'll start this. I don't know that we'll see how long it runs. It might be an astronomical amount of time, because now, before we went from 1 to 10, we added 9 million. We just added 35 million, and those are all going to be, on the order of tens of millions longer than the ones we had before. So this is where exponential math just comes out and crushes us. And so this might run in a matter of minutes. I don't know, but it's not going to be fast, and it's going to be pretty brutal. So I'll probably pause the video here and let it run for a while, but I'm not even sure we're going to get to a solution on this. Clearly, the solution that solves in half a second is better. So we'll go with that. But yeah, in case I don't come back, thanks for sticking around till the end, and I'll talk to you next time.